Hello and welcome. This is the Audio Engineering Society's New York section event meeting for July. And my name is David Bialik. I am a member of the committee that plans the events here. And today we have a treat. We wanted to discuss podcast acoustics. My first thought was Sam Berkow. And they said, do we need to get some other speakers? I said, when you have Sam, you don't need anybody else. Sam is a noted acoustician. Whenever I call him, he's on a different part of the world. The other day, I think I was speaking to him, and he was in California. He did the Palms in Vegas. He did jazz at Lincoln Center, and he is a Parnelli Award winner, and he is probably one of the most knowledgeable people there is on acoustics. And I want to introduce Sam Berkow.
Hi, everybody. How are you? It's funny, you don't hear anyone saying hi back. So today's topic is the acoustics of podcasting. And so I thought we'd start by asking what makes a podcasting studio different than a regular traditional recording studio for music or speech even. And the most important difference is that in podcasting, almost everyone's listening on headphones. When you have podcasts that are one person, you can do a wide range of monitoring, but the monitoring is less important than the environment for the microphone. Relaxed conversation. A lot of podcasts have 2 or 3 different people speaking, and the idea, like David and I are in different locations, the idea of being able to have a relatively neutral environment with similar noise floors makes it more cohesive. So the idea of building a space that's designed for the microphone as opposed to the monitoring rig is a little bit different than traditional studio design. Also, podcasting studios tend to be a good bit smaller than traditional studios. So you're starting with a smaller space and you're less worried about creating a sweet spot mix position than making most of the space comfortable to speak in, comfortable to record in. Make sense, David?
Yes, I'm sorry, I muted my mic that I can better pay attention to the master.
Lord, you got to stop that stuff. So there are a number of design issues. When you're building a room for monitoring, you're really worried about the room shape, the modal response of the room, the tonal balance of the room. And these things matter in a podcasting environment, but it's more forgiving. The idea that a smaller room has more modes that are potentially problematic is very real. Turn off my phone, of course.
We're not even going to ask what that ringtone is.
That's my cousin, believe it or not. He has his own ringtone, and I didn't know it wasn't muted. I had it on vibrate, but I'm going to turn it all the way off. Okay, great. Sorry about that. In the meantime, we're talking about starting out to design a podcasting studio. So if you have a room, the part of the frequency range that's affected by modes is really given by a very simple equation, 3C over D. C is the speed of sound, and D is the smallest representative dimension of a room. So if you say 3,000 divided by, let's say, 10 feet as a representative dimension of your room, then you know everything below 300 hertz is going to be modal, more or less. And that's well within the speech frequencies. You're looking at me funny, David. Your voice, I can't hear you.
I'm trying to understand the formula now. And when you're saying the dimension of the room,
Smallest representative dimension of the room.
so would that be the square foot area, or
No, it's a single dimension. What I like to do is say, if you put your fist in the middle of the room, how far are you from a surface? And then if you put your fist up in a corner of the room, how far are you from a typical, surface? There's a whole mean free path study, but it's really, it's an approximation formula anyway. The actual formula is Manfred Schroeder is credited with, it's called the Schroeder frequency. And if you think of your room is affected by very, very low frequencies, pressure waves, like earthquakes, differently than from internal excitation modes. And that's different than reflections. And what happens is, if you calculate the modes, and there are three types of modes, axial modes, which are two walls, typically parallel, floor, ceiling, sidewall, front wall, back wall. Those are your axial combinations. Then you have your oblique modes and your tangential modes. Your tangential modes are 4 walls, and your oblique modes are 6 walls. And the idea is that if you do a little calculation, and there are lots of modal calculators, what you see is there are more and more modes as you get higher in frequency. And they start to overlap so much that you can't excite just one. So it's really about the density of modes, and 3C over D gives you a rough approximation. So it doesn't really matter if you're precise with D. So let's just do an example. If you say that the speed of sound is roughly 1,100 feet per minute, and you divide by 10, right, for 10 feet, 3C, 3 times the speed of sound is 3,300, is 330 hertz. And if you make it 11 feet, it's 300 hertz. It doesn't really matter that much, because again, it's an approximate range. So you can say below 250 hertz, the room can be modal. And when you measure a room, you see these very clear peaks and valleys. So the smaller the room gets, the more important low frequency absorption becomes, because you'd like, for speech, you'd like to have, 150 hertz up be well behaved. You don't want every guttural sound booming at you. You'd like to be able to have a more sophisticated, tonally balanced sound. So the best way to absorb low frequencies is with very thick absorption or panelized absorption. There are a number of companies that make really good low frequency absorbers that come in 4x4 or 8x4 panels that you can put on a wall. And we've recently been hanging higher frequency absorption panels in front of those panels, because they let low frequencies through so easily in the higher frequency range panels. One thing that surprises almost everyone is there are only really 3 things you can do with a sound wave, right? You can try to absorb it, you can scatter it, which is diffusion, or you can redirect it by re-aiming walls. In small podcasting studios, typically we try to scatter mid-high frequencies where it's really efficient and absorb some low frequencies. You with me there? Great.
yes? Sorry, I'm
Pressing the
muting.
space bar.
I'm muting to not cause any acoustical noise to the acoustician.
Great. By the way, if there's anyone joining us and you have questions or comments, feel free to text them away here, and we can certainly.
Yes, please put them in the chat. We are monitoring the chat, and we will try to get to all questions asked.
That's right. And if anyone has a good joke, you're certainly welcome to offer that too. David will tell it. 43. Anyway, I was going on diffusion and absorption. now there are lots of companies that offer all sorts of different diffusion type products. And what's really nice is that you can get diffusion over most of the speech frequency relatively cost effectively. And it doesn't take much to find absorption that, or I'm sorry, diffusive surfaces that are only 3, 4, 5 inches thick that are really effective down to 500 hertz, 600 hertz, somewhere in there. And that really, if you can scatter some of those sh sounds in the 1 to 3K range, the SHs, the CHs, those sibilant sounds that are often so problematic in voice and speech recording. You don't really want sizzling podcasts. The idea is to engage the listener. So the acoustical environment is mostly dealt with surface treatments, and they tend to fall into low frequency absorption and mid-high frequency diffusion. And you can combine them. As I said, we often put low mid-frequency or mid-low frequency absorptive materials behind mid-high frequency diffusers. And that can be very cost effective and very pleasant to look at. We've been working with Richard Lenz at Real Acoustics, but there are lots of companies making both one-dimensional and two-dimensional diffusers. The one-dimensional diffusers tend to scatter sound horizontally, and that's very effective. They tend to be very effective. The two-dimensional scatter sound both horizontally and vertically, and they're getting more and more efficient. So really, there's no compelling reason to use one or the other in a podcasting environment. I think that in a podcasting environment, the idea is to make the room not so dead that the people feel comfortable and the room has some tonally balanced ambience.
Sam, could I ask a question?
Of course.
Now, when you're in a podcast studio, it's a small space, and usually it's made for 1 to 3 people. Most of the ones I've been in, and I like to say that human beings are acoustic sponges, because we're absorptive unless we're wearing something very reflective like a silk outfit or something. How do you take into account when planning a room the acoustics of for when there are people and there aren't people? Is there a formula to calculate for humans?
Believe it or not, way back when in the 1960s and even before that, there were a number of people who measured reverberation in rooms with people and without people, with padded chairs and with hard chairs. A fellow named Costin did a series of coefficients for concert halls that are still used for the effect of the presence of an audience acoustically. Interestingly enough, we also account for people in terms of heat load. And I was about to segue from room treatments into air planning and heat load planning. But to address your concern, your issue is people are effective in mid frequencies. They don't really affect low frequencies very much at all, unless you get a lot of people. In most podcast rooms, people provide absorption in the 400 to 800 hertz range, a good bit. And so when the room's empty, you get a little bit more build up in those frequencies when they're there. But below that, people don't have much effect in small rooms at all, actually. Anything else, David?
No, thank you. You've just explained something I've been trying to figure out for a while. Thank you.
You know, one of the things is how much heat do you think people give off? And one of the interesting things is that depending on what they're doing, like how much they're yelling, it's funny. One podcasting studio is a guy who likes to wave his arms and rant and rave, and the room was getting hot, and there really wasn't enough cooling. And, you know, this guy was sweating and screaming. And I was like, how much air are you providing? And it turns out they had turned the fan onto its lowest setting because they had designed a noisy system. They didn't want to put more air to raise the background noise. So having a design target for air conditioning is an important part of podcast studio design. And the way that process starts is get your heat load, figure out how much equipment you have, figure out what you want to. I'm reading the chat window that just popped up. Figure out how much heat load you have, then figure out how much air it's going to take to dissipate that heat load. We'll come back to this in a second, but to go back to I didn't think a good ratio of absorption to diffusive surface area is a very
Sam,
interesting question.
Sam, the question is, for a small room, what's a good ratio of absorptive to diffusive surface area?
Right. I answer that this way. There's a rule where that was developed by Leo Baranek for tonal balance. And this is good for small rooms and big rooms. And what it says is, if you take the 1,000 hertz frequency range, the 125 hertz frequency range shouldn't be more than 40% longer, right? So if you have a 1 second room at 1K, you should have a 1.4 second room at 125 hertz, all right? Very simple rule for tonal balance. We've taken that a little bit farther, and we've said, take your 125 hertz decay rate and calculate or measure the 500, 1K, and 2K values, average those, and then we apply 1.3 ratio to make the rooms sound tight and tonally balanced and not boomy. So there's no specific ratio, but what we try to do is we try to pick enough absorption and enough low frequency absorption and mid-low frequency absorption to achieve that tonal balance, and then use enough diffusion to control any reflections that might be coming back to the mic. So the diffusive treatment is more, the amount of diffusive treatment is more based on the amount of reflected energy in the room, dictated by the room shape, which in podcast studios is often rectangular or catch as catch can, rather than the fancy shapes we use with for studios.
Okay, so let's take one step back then.
Sure.
As a podcast studio, we have to deal with reflective surfaces too, because most likely in front of your microphone, you have a monitor. And nowadays, people are even putting in these curved monitors.
Yeah.
So that must be a whole, the curved monitor versus the straight monitor versus the slanted monitor. That's got to be a big issue.
It's funny because we just looked at a curved monitor and we put a microphone in, and the microphone had adjustable pattern. And it was amazing because when it was in Omni, you could hear the harsh reflections of someone. And I was reminded of the pop filters that people use for vocals, the curved foam pieces that go behind the microphone. And I'm like, they didn't like the sound and the variation in head location for the cardioid configuration, and they hated the hypercardioid and the Omni because they were getting these reflections off the curved monitors. They were focusing back to the microphone, and the people were noticing, particularly with S's and T's, that it was really a problem. In the case of monitors, we like to put monitors up a little bit higher and have them slant down. And so people are looking up a little bit and the camera's below, and that seems to work out nicely. Particularly if it's for guests, we put it off slightly to the side. And so we try to have an absorptive or a diffusive space directly in front of the talker so that you don't hear the mic. I'm using a mic today that's in a figure eight. It's a ribbon mic, so it's hypercardioid by design. There's not really much you can do about it, but I've angled the far way away from my screen. So the screen should be in the null.
Okay, and my screen is directly in front of me, and I'm using an RE20 right in front of me.
And the RE20 is a cardioid, correct?
Yes.
Right, so it should be rejecting a fair amount of off-axis.
And it is. If I go off axis here, you
Right.
can't hear me.
Great. So I think that the key thing about absorption, I don't know that there's a specific ratio I look for in terms of areas, but I do look at tonal balance and the overall amount of absorption. And one thing that people don't really look at very much is the amount of absorption, particularly mid-frequency absorption, that diffusers can apply. That's really interesting. We really looked at this. We looked at a large space, an amphitheater that holds 20-some thousand people, and the roof was too low for really big shows. So we literally picked the roof up and 26 feet and added it up. And I was very concerned about these long reflections now that we're going to be coming down from the roof and back to the front of the audience and the stage. So we put huge number of big, heavy, mid and high frequency diffusers. And when we tested them in a chamber, we found that they were offering a lot of mid-low frequency absorption and really tightened up the sound in the amphitheater. Really worked out nicely. You get the same benefit in a small room. Unfortunately, they don't provide a lot of low frequency energy. So you have to go to a different type of absorber. People are very effective using plates with what are essentially rubber springs behind them. I'm a fan of the base mod 4848. There's a number of companies that make really good low frequency, and we're talking here, 70, 80, below 100 hertz absorbers, and they're well worth having. The other thing is that if you can get your materials away from a wall, using a soffit is one thing we really like to do. We treat all the surfaces of a soffit so that you get high frequency, mid frequency absorption as you would expect, but you get much more low frequency, mid-low frequency absorption, because if you have 2 inches of fiberglass in airspace, 4 inches of denser fiberglass, a wall, then the sound's coming back through 4 inches airspace and another 2 inches in a soffit. It's really a wonderful bass trap. And when I say bass trap, I mean mid-low bass trap. And for podcast studios, soffits or false ceilings with slots to allow the low frequencies up, and putting 6-8 inches of absorption is very common in a ceiling if you have high ceiling heights.
What are you, since you're talking about materials, I'm gonna throw this at you, even though it's been recently in the news. What's your feeling on these acoustical screws that have been articles have been written about?
I just wrote a response to someone online. I love innovation. I'm a big fan of innovation, right? Like I want to see every new trick there is. There's a company that's making a new product called SoundGuard, which is a split stud with a neoprene gasket built into the 2 pieces of stud. So instead of having 2, 3, and 5/8 inch studs with an airspace behind them, they're taking what would normally be an 8-inch assembly and they're making it less than 3 inches wide and giving you the same performance acoustically. I love that stuff. The problem I have is that this acoustical screw idea, it may be great, but we don't know yet because they haven't released any real data except for saying it reduces sound transmission by 9 dB. Well, I'm not exactly sure what that means. Is that at one given frequency? They published a plot, but you couldn't see the vertical scale, and you could see the frequency scale on the bottom, and there's no effect below 250 hertz. Well, if you ask most people, below 250 hertz is where 75% of sound problems live, particularly with thumping music. In office environments, if you could find a solution that would give you extra attenuation and extra transmission loss, it would be great. It's my opinion, and I could be wrong here, that this is a bunch of guys in Sweden or Norway, wherever they are, with a connection to MIT, and they're looking for a deal. They're looking to market this to some company to license it. And I'm like, why are you on social media? Why aren't you going to venture capital firms and doing a dog and pony show like everybody else? Go to, 3M or, US JIP or, someone and say, Hilti, hey, here's our product. Can you manufacture this cheaply in the bazillion part numbers?
Well, that brings up something that I've always said is I hate how the term acoustic is misused, specifically acoustic ceiling tiles. There's nothing acoustic about them.
Oh, no. I don't mind that one as much. But when people talk about acoustics, they confuse room treatments with acoustic isolation. And acoustic ceiling tiles, there are people who make high STC ceiling tiles. And an architect I know is a very talented guy, put these in and said, I don't know why they don't work. And I went into the room and I looked, and there's giant return air grills. And I stood in a spot, this is a true story. I stood in a spot, looked up through the return air grill and saw a transfer grill to the lobby. I could see the chandelier. And I'm going, you're kidding, right? Like, you have line of sight to the lobby. And their CEO walked in, could hear people telling a joke in the lobby, and walked out of this very expensive conference room. And you run into the same thing, like very obvious things become problems. Acoustical ceiling tiles, have ratings. They have noise reduction coefficient ratings, NRC ratings. They have absorptive ratings as a given frequency, absorption coefficients. And it's very easy to know if they absorb a lot of sound or not. 0.85 and above is an NRC, is a good tile. Lower than that is not such a great tile. It's easily to tonally imbalance a room. I won't embarrass him, but one of my favorite recording and live engineers built a home studio, and it was boomy. And I said, okay, let's take these panels off the wall and just lean them up against the wall. Now it won't be so boomy. And he's like, what? And I did it. I started pulling panels off the walls. What are you doing? I'm like, you've got them tight up against the wall. You need at least an inch airspace. Now, there's been a bunch of research that people have done that suggests that more than an inch or an inch and a half, you don't get any more benefit. But if you look at 2 inches of fiberglass, the absorption coefficients are dropping off rapidly after 250 hertz. And so you may have only a third of the efficiency at 125 hertz, but when you pull it off the wall an inch, you get extra efficiency at those frequencies. And if you put additional absorption behind it and go to 4 inches of absorption, you can get a more effective absorber in the 125 hertz band, which is a critical band in terms of tonal balance, as I said before.
When I first started working and building studios, I was told by the engineer I was working with, the denser the better on the walls.
Yeah, that's an interesting thing. Denser fiberglass tends to absorb low frequencies more efficiently, but it also reflects higher frequencies. And I don't know if you remember a gentleman named Greg Lukens, but Greg is blind. And I didn't know he was blind. No one mentioned to me when they sent me to go meet him and demonstrate SMART that he was blind. And he was bent over this rack. And I said, hi. And he said, I'll be with you in a minute. And he kept me waiting for 15 minutes. And I was like, this is sort of annoying. He's got his head in a rack for 15 minutes. He turned around and reached out to say hello and reached in the wrong direction. And I was like, oh my God, this guy's wiring a rack and he's blind. I was like, wow. And it turns out he has amazing ears. And as soon as I made a noise, he found the right direction. But Greg walked into a studio that we had designed, which is called Tonal Park now. It was Air Show Mastering East in Tacoma Park. And he's like, you're using high frequency diffusers there. You're using high density absorption there and lower density absorption there. And he was hearing the 8K reflections. And he was dead on. I mean, he knew it, and literally blind, forcing me to listen even harder and more carefully to high frequency reflections. You have to be careful with 6-pound density fiberglass. What we do in soffits, where we put multi-layers in, or if I'm putting multi-layers in, we'll often use 3-pound or 4-pound density fiberglass as a front layer and a 6-pound density at the back.
Way back when I started, I was working in a studio that was built in the 50s, and the studio walls were all cinder block, and they kept saying density is better, and and of course the acoustics changed because it had maybe 20 or 30 years of coats of paint on it, but I found that as long as it wasn't a reflective paint, you basically had a pretty absorbative room, and it was pretty isolated. Would you agree?
Well, that's the beautiful thing. This is people who are confusing room treatment for the acoustics with the room with isolation. Nothing beats mass for isolation. You have two tools when you're trying to isolate a room. You have mass density and you have resilience or discontinuity. So, for example, it's very common for us to use multiple layers of sheetrock and put a viscous damping layer between them. And isolated floors, we often use a resilient layer like we use kit pads, compressed fiberglass pad pucks. There are 2-inch centers that are on either 16 or 24-inch centers. So you have these 2-inch cubes and they're spread out over a room. And we put down a layer of plywood. Then we'll put down a layer of a discontinuity layer like a honeycomb. And that's 5/8 of an inch. And then we'll do a sandwich of plywood, cement board, and plywood. And the reason we use the cement board is like Hardy backer board or some other material like that is you're screwing 3 layers together that are sitting on top of your honeycomb. And you are saying, okay, this is the wave is going to see this very dense sandwich where the cement board has double the density of the plywood, and mass density is just the weight per square foot divided by the thickness. And that's really what stops sound from going through walls. Then you get into penetrations. And we just came up with a case where someone had built very expensive walls using isolated clips. And when you have an isolated clip and an isolated wall or isolated ceiling, if you cut penetrations in it and then you cut penetrations that sound can get out or get in, you're creating paths for sound to travel. And so mass is important, but if your door is leaking, what difference does it make how good your walls are, right? As far as the room treatment goes, cinder block's never my favorite because it tends to be very reflective, except at very high frequencies because of the rough finish. You put enough coats of paint, it just gets very reflective. But it's very massive. We often grout fill those cinder block walls to give them even more mass to keep sound, like between a stage and a recording studio, like we did at E-Town Hall or at SF Jazz Center, where we have a performance space, and then there is another performance space below it in the lobby, below the rake seating.
When I was in college, I had a great professor for acoustics, Lynn Claudy, who's now a VP at the National Association of Broadcasters. Mm-hmm. And he told me to test reflectivity in a room. If light reflects off of it, sound will reflect off of it.
Yeah, I mean, that's
the good test?
No. Absolutely not. It's the mirror test, which is you take a laser and you put a mirror up and you see where it bounces. And you can do this electronically in 3D modeling. It's easy. Angle in equals angle out. That is a first order approximation, and it's very useful for the first couple reflections. And a very famous friend of mine is an acoustician, ran an early version of one of the modeling programs. And he said, it's been running for 2 days. It's doing 12th order reflections. We're going to see every possible reflection. And I'm going, you realize after third order, it's no longer really anywhere near accurate, right? Because if a wave, you're just assuming the wavefront's following an arrow, right? Well, what happens if that wavefront hits towards the edge of a panel? You have diffraction, right? And the energy goes off. What if it hits a diffusive surface? Then it gets scattered. So what if it hits an absorptive surface? And what you start doing is you start realizing that the more hits you have, the less accurate your model is. So really, image casting models or ray tracing models are really good for first, second order reflections. They're useful to see what third or fourth order reflections are. But above that, you're really sort of missing the ball game. Okay. Ooh, we have someone serious here. Can't mess around.
I want to read a question from Joyce Lieberman.
Yeah, by the way, if we get it wrong, Joyce will let us know. She can be mean, very mean.
Joyce knows her stuff.
Yeah, no kidding.
At WHYY in Philadelphia, she has many producers and reporters reporting their pieces from home. Is there a low-cost solution for low-frequency absorption and high and mid-frequency diffusion? Do they need to cover all their four walls? I've heard stories of recording in closets with their clothes absorbing some frequencies.
Joyce, let me just say, I believe everyone should come out of the closet. Be who you are.
Sam, that's going to be the soundbite from this.
I hope so. That was a joke. The price of, first of all, no, you do not have to cover all of the surfaces of your walls and surface. You want to cover enough to do that tonal balance. And the reverberation equations are so very simple, and there's lots of spreadsheets. But if you just take a look at getting some absorption on the walls where sound is likely to bounce, I like to do diffusion above where people are talking. There were a number of one of the big network studios where they were doing a morning show. The talent was very unhappy with the sound of the room. And we just went in and put a bunch of diffusers above them, painted black. They can't see above the lights. It was above the grid. And they came in and like, what happened? It's fixed. And I'm like, yeah, it's not that hard to figure out. They felt like they were not getting anything back from the room. And when the ceiling was hard, they were getting too much back from the room. So a mid-high frequency scattering device. There are lots and lots and lots of diffusive surfaces that come in at like $15 a square foot or less. And so there are a combination of absorptive and diffusive materials in that same price range. I think that the lower the plate absorbers and the lower frequency absorbers tend to be a bit more expensive still, but the price has been falling dramatically over the last 5 or 6 years. So it's been really great that these tools are available. For podcasting studios, we often do things where we'll put raw fiberglass panels on a wall and then hang a light curtain in front of it. If you can afford a 22-ounce heavy velour, it sort of gives a nice look behind something if you can do some sort of drape and then put panels behind it. In a recent rock and roll venue, I bought a bunch of 8-foot tall by 4-foot wide panels that absorb tuned to various frequency ranges. They tend to be about half an octave wide in general. And we had them at 54 hertz, 68 hertz, 74 hertz. all the frequencies we thought were going to be problematic on stage. And the reason was we were trying to make the stage more comfortable for microphones, to get some of the boom out of them, instead of having to low cut everything and hope we got rid of it, to get rid of it acoustically and make the stage easier for people to hear. We did the same thing at the SF Jazz Center. We've done the same thing in some podcasting studios. I hope that answers your question, Joyce. Can you tell us something about Smart EQ? Smart EQ. I don't know anything about Smart EQ. I know about Smart. Smart is a program I developed. It's now owned by a company called Rational Acoustics, and they're doing all sorts of fun things with it. You can go on their page and check it out. The original acronym SMART with 2 A's was developed, or came, what's the word I want? Created by the woman who was my girlfriend at the time. We later got married. Her name was Susanna, or is Susanna DeBaca. And we were looking for a name for SMART. And what's one of the guys I was working with said, what about system equalization and acoustical correction? And that's his acronym for that was CQUAC. And I was just like, no, it sounds like an ocean going duck. We're not going to do that. And Susanna literally said, I said, I'll give dinner for 2 or dinner for 4 or something to anyone who comes up with a name. And she goes, tell me what it is and what it does. And she took a piece of paper. I said, it's a sound thing. It's measurement. It's acoustical analysis. It has a real-time tool. And she looked and had literally said SMART down the side of her page. And she said, I think we should call it SMART. And so I owed her dinner. SMART is a dual channel transfer function analyzer. And it has lots of different parts now. It measures both the multi-time window transfer function and the impulse response of a room. The transfer function is the difference between the signal you send out and the signal you get back. But the way we hear is very different than a simple measurement like that. Your ear has different time constants. You hear high frequencies much faster than you hear low frequencies. And a number of famous acousticians and people who studied psychoacoustics have documented this. Kaushi Ando is one. The folks from B&K knew this a zillion years ago, back in the 60s. And what SMART does is allows you to measure the high frequencies of the direct sound coming to your microphone, and then increase the amount of influence that it lets into the measurement of the room as you go down. So you're looking at one curve across the frequency domain, the low frequency portion includes more of the room effect, and the high frequency portion isolates the high frequencies and the speaker. And that pretty much mimics how you hear. The first commercially available system to do that was SIM from Meyer Sound. And SIM was an awesome tool at the time because it let you measure these multi-time window transfer functions. The downside to it was very, very costly. And it didn't do room acoustics measurements, impulse response, which is not hard to understand. The Meyer Sound is a loudspeaker company. They're not a room acoustic company. And I was working at Artec and wanted to measure rooms. I wanted to measure reflections and dispersion of sound in rooms. And so I developed SMART to give us the tools we wanted to measure sound systems and also room acoustics. 2 people I was working with at the time, one is Alexander Ewell Thornton. We call him the Deuce. Thorny is one of the most interesting people I know. He was Pavarotti's sound guy and did all the 3 tenor shows. And he was someone who I was lucky enough to meet, and we started a conversation, and he and I started the SIA Software Company that wrote SMART. And the other one was, unfortunately, the late and very great Dr. Don Pearson. Don was the founder of Ultrasound, which was basically a company set up to service the Grateful Dead. And Don was the system engineer for some 3,000 Grateful Dead shows or something like that, Grateful Dead and related shows. And Ultrasound was always looking for better tools. And Don was always looking for better tools, both to understand room acoustics, but particularly to equalize sound systems. And so I was inspired by those guys to build SMART. And I sold the company so I could continue designing concert halls. It really came down to build more software, design more concert halls. And I got the good fortune to have the opportunity to work with Wynton Marsalis for a number of years, building and designing Jazz at Lincoln Center. And we had a blast doing it. And I still consider it one of the highlights of my life to be around Wynton and his energy and his amazing talents in performance and composition and vision and everything.
It's a beautiful facility.
Yeah, and he's a great guy. He's just one of those people that walks a little bit off the ground, I think.
Getting back to the podcast topic now.
Yes.
Okay.
Going back, I wanted to talk about air conditioning for a second.
That's what I wanted to talk about, because the biggest problem I have when I go into a place where a radio station says, hey, we need our podcast studios fixed in these people's homes, and I find out I'm hearing from the air conditioner vents left and right.
Yes.
And is there a cheap and dirty way to get those vents to clean? To not make noise without turning off the air conditioning?
Yes, there is. Let's start at the beginning, all right? The best air conditioning system is one that's properly designed. And the proper design process starts with figure out how much heat you have to move, right? So you have a room, an enclosed room, and you're going to push air in. That's the supply side, and air is going to come out, right? That's the return side. Now, what typically happens is instead of that air coming from outside, getting chilled, coming in, getting pushed out and going back outside, there's a loop, right? And that's a big problem because a lot of podcast studios put a unit on the wall that only sends chilled water, like a split unit has a condenser outside and it sends chilled water, but no fresh air gets in. And so now they're counting on you opening the door or having a gap under the door so that some fresh air gets recirculated. The problem with that is that we don't want a gap under the door because we want to have a room that's sealed so people can talk outside of our studio and we don't hear them. So now you have to find refresh air. So what happens is some of the return air comes around and gets refiltered and gets added some fresh air and comes back in. That's great. How much air? Well, what you need to figure out is the cubic volume of your room, and you can figure out what your heat load is. And you can figure out from the heat load what the temperature difference is. Typically it's 8 to 10 degrees between the chilled air on one side of your unit and the air coming in. And you can figure out how many air changes you need and how much fresh air you need. And that gives you the cubic feet per minute of air, CFM of air. And now you know how much air you need. Slow air is quiet air. So what we do for most things is most rooms is we say, look, a podcast studio doesn't need to be deadly quiet, but a nice target is NC 25. NC is noise criteria. That's the basic background noise level in a room with the air conditioning on. And you can measure the levels with the air conditioning on, turn the air conditioning off, measure the levels, and see how much it's raising the sound level. Now, we say we would like the air to come out of the vent at 300 feet per minute or less. So what I tell people is the first thing you do is get rid of the grills that you have and just unscrew them. Because if the air is coming too fast, take the grill off and it will reduce the turbulent noise, the noise from the air turbulence. Secondly, try to slow your fan down, right? Chill your room before it gets used and have your unit run on its slowest setting so it maintains temperature as best it can. Lastly, build a trap so that instead the duct coming just out of the wall, flat with the wall, have it come out and turn both directions and have grills on the side. So you've slowed the air down because now it's hitting a lined piece of duct, and a T like that is $200, $300, right? That could be supported from a ceiling or from a sidewall. And it's redirecting the air, absorbing some of the sounds coming out. And the air, because it now has two outlets on either side, is half the speed of the one outlet on the wall. So you've slowed the air down, you've absorbed some of the sound, and you've made the room quieter. Making rooms quiet and giving them enough HVAC or heating, ventilation, air conditioning horsepower to maintain the heat load is a critical factor in room design and very often overlooked. The other thing is where your ducts come into your studio and go out of your studio on the supply and return side is a weak link in your isolation because it's a hole in the wall with a piece of metal going through it. And that's where we put inline duct silencers. And inline duct silencers are very cost effective these days. A 3-foot duct silencer can be had for $500-600. And they're easy to install, and the resistance, if you will, of a duct silencer, which is just a piece of duct with some fancy insides to block sound, is known as the pressure drop. And there are a number of very low pressure drop duct silencers that work exceedingly well. I would say that I put many a duct silencer salesperson's grandkids through college. we specify a lot of duct silencers. It's crazy how many duct silencers we specify. But they really work well and they're very cost effective.
What about also if you're building from scratch, because obviously you can't do it afterwards, making sure that the ductwork is isolated from the building by putting
it's almost impossible to do that. You can hang it on isolated hangers, but what happens when it comes through the wall? It's going to touch the wall. So you can wrap it in neoprene and do a seal. For those of you who are going to wrap ducts in neoprene, here's a little hint. Do not use a silicone-based sealant around it because neoprene's a type of rubber and silicone eats neoprene and it creates black gunk that you will never get rid of and is a nightmare. So whenever you use a sealant around the neoprene-based seal, always test it. Take a little piece of neoprene, put the sealant on it, go away for a couple hours, come back and get a glove and touch it and see if it's not goopy, in which case you don't want to use that sealant. You have to use a compatible sealant. There are lots of ways to isolate ducts. You can use flex duct connections. Again, it really comes down to the goal of where your isolation is. If you're wrapping the ducts, you can wrap them in different types of insulation. We use a high transmission loss isolation material that's a doped vinyl. It has little flecks of metal in it to make it denser and comes with and without fiberglass. Any other questions?
Michael Jung is asking, would making the duct non-linear help reduce noise?
I'm not sure what making the duct non-linear means. Adding turns definitely does help if the turns are rated for the velocity. If you're talking about adding turns in ducts come in a bunch of variations. There's lots of different types. If we're talking about metal duct, turns can either be 90 degrees or radiused. Radiused ducts can have turning vanes in them or not. If you use turning vanes and you use high velocity, the turning vanes will whistle. If you don't have turning vanes, you can get turbulent noise. So you have to design the right type of turns. That definitely does. The other thing is the thickness of the sheet metal used matters. Most ducts are 20 or 22 gauge sheet metal. If you're going to put it through a wall, I like to use 20 gauge because it gives you a better seal. It doesn't flex as much. And well, we almost use exclusively lined duct for once we get close to a studio space.
And what is the duct lined with?
It's with a special type of fiberglass called duct liner board. And duct liner board has a woven fiberglass face. I'm making the woven fiberglass face symbol here. And what happens with the fiberglass face is that it won't shed fibers. A lot of people have concerns about breathing fiberglass, and I share those concerns. But the companies that make duct liner board are required to test it in a chamber to show that it won't shed fibers up to 4,000 feet per minute. And if there's 4,000 feet per minute coming in your duct, get out of the building because there's a hurricane, right? I mean, that's such a high number. We're never going to see that in the real world. We deal with like 500 feet per minute in most 500 to 700 feet per minute in most ducts that are supplying rooms. And we try to get down to 300 feet per minute or less at most outlets. We like to dump air in, let it get carried across the room. The other thing is that you can come into a room, the isolated shell of a room. And one of the things I like to do is come down with an elbow so that you're facing downward, and then come all the way down and either put a linear diffuser on the wall vertically or put a standard diffuser at the bottom of the wall and use that as a supply low and either return high and have the sound travel along the wall and then out, or you can supply high, have the sound, the cold air just drop down and the return pull it from low. Either way works. They both work effectively well. In old concert halls, they used to have underseat return air or supplies, and then supplies were under the seats, and they would blow air from fans over ice. We had that in a big temple in Los Angeles where we just blew the air in through these holes, and then up high they were pulling the hot air out. But in a podcasting studio, it's so small, it doesn't matter if you can get the air in, but having slow air and having it pull across the room basically is the best you can do.
And the one thing I could suggest is, because I saw this the other day, if you're going to be building a podcast studio, think where your microphone is and try to have it as far away from your vent as possible, because the last thing you want to hear is air moving.
Right. Well, what I was going to say is that if you design to NC between NC 20 and 25, you should be great and you shouldn't have a problem. The NC values are quite a good metric. For performing arts, Rose Hall at Jazz at Lincoln Center is like NC 5, and it has a subway underneath it. There's actually a picture I can post of Don Pearson. I took Don Pearson to see the isolators on the columns, which are a piece of steel plate like a 1/4 inch thick or 1/2 inch thick, and then a rubber pad, then a steel plate, then a rubber pad, then a steel plate, a rubber pad till it's about this thick, and then they pour the column on top, and the rubber pads bow out at the sides, and they measure it in kips, which is some number of tons of pressure that these isolators take, but they go right down to the subway, which you cannot hear in Jazz Lincoln Center. And Rose Hall, the whole hall's floating on these isolators.
I've often wondered, will the rubber in those isolators eventually dry out?
It's good for 100 years.
So in other words, it's someone else's problem.
Well, 80 some years from now, I've left a note. I actually laminated a note to the people swapping them out with a picture of me and Don and Winton and a bunch of people in hard hats saying, these are the people who put these here. And thank you so much for replacing them. They test the durability of rubber, and it's very interesting because that was a big question. Um, uh, do we have any other questions from our audience? How long are we going here? You said about an hour. Do you want to?
Yeah,
I'm happy to answer some questions if people would like.
we can go a little longer, but first I do want to thank Roy Shamir and Angela Piva for helping set this up today. And I also want to thank Sam Berkow for making the time for the New York AES section. And we'll continue talking for a little bit.
He an AES member, by the way. One of the best
Yes.
things I ever did was start going to AES conventions.
And the worst thing you did was give me your phone number.
Nah, that's not the worst thing I've ever done. I've done some pretty horrible things. No, I encourage everyone to participate in industry section meetings. I've lectured at more than a dozen around the world. It's been great fun, and you get to meet amazing people. And one of my favorite things is I was asking a question, and I had actually researched the question. It was when DSPs first came out, and some guy was showing his DSP unit, and I asked a question about it, and hold on for a second. We have a question about this.
Yes, Michael Young has asked you, how do you replace those plates under the Lincoln Center if they report if the columns report on top of them? And my feeling is not easily.
No. It turns out that it's hardly as horrible as you think. I don't think it's going to be as hard. They use the same way they replace any other column. What they end up doing is jacking up the slab. They put heavy duty bolts in the slab, and then they spread the load, and they take some of it out and put, they cut away a piece. And those guys are, the people who do that stuff are all so amazing. I mean, it's really a skill. Hang on,
And you really don't want to be the guy that dropped Lincoln Center.
Yeah, you really don't. I wouldn't want to pay their insurance. How's that?
Okay.
Hang on for one more second. I'm going to see if I can find this. I think I can. I can't promise, but I found it here, and I am sure that I can find this picture quickly. And you know what I'm going to do is I'm just going to put this over here. I'm going to say share screen, and we can pull up a bunch of pictures, desktop number 2, and you should see desktop number 2. Yes?
We see a desktop. We see you moving your mouse.
You see lots of little pictures?
Yes, we do.
Okay, let's see if we can find Pearson in there.
Obviously, this was not rehearsed.
This is not only not rehearsed, this is totally impromptu craziness. This was not what I wanted to do. Let's go here.
And while you're doing that, JD Wong has written, some music recording studios are pivoting towards podcasting. Do you know of any examples of studios using a live room, or would a vocal booth be more suitable? And I do know of some podcasting facilities using live rooms.
Me too. You want to tell a story? I have a great story, and I can even pull up pictures of it as soon as I find this picture of Don. So I mentioned Don. I want to pull this picture up. There must be a picture of Don in here somewhere. I just put this in here the other day.
Yeah, I think you even posted it on Facebook.
I may have. I love that guy. He was so good to me. One of the reasons that I try to do these podcasts and AES meetings and such is that Don encouraged me to do that because he was so generous with his time with people. Don really believed in paying it forward. And so
it's one of the wonderful things of AES. I will never forget sitting in the hall talking to Leo Baranek and realizing, hey, this is Leo Baranek.
I know this picture is here because I just saw it. You know, I've been going through and um, trying to categorize these pictures for years, and it's always hard to find time to do that stuff.
Just make sure whatever picture you can show is a picture you want to show.
Oh no, there's nothing in here that I'm happy to show. I'm happy to show any of these pictures. All right, let's try one more time. Let's see if it says, if I can just say Don. See, there's Don.
There it is. Third row down to the right.
This is, yeah, Don and Sam. No, that's a party picture of Don.
Oh, okay.
All right. Well, we won't get to see the isolators. I'll post it on the AES section page. How's that? So you can see. Here is just a picture of Don Pearson.
Could you give us a? I know this is impossible. A 3-minute bio on Don that people know why you're referring to him so much.
Don was the co-founder of Ultrasound, which was a company dedicated to, I'm trying to, now I want to get back to my stop share. How do I do that? Here?
I believe on the
Oh,
bottom
there
of
it
the top.
Right. It showed up on my other screen. There we go. Don was a co-founder of Ultrasound, and I had two main mentors in my career. One was Russell Johnson, who I learned concert hall acoustics from, and the other one was Don Pearson, that I really learned a high-end sound system design from. And Don had so much practical experience. And when I started out, acoustic measurement was a scientific and academic endeavor, not a tool for people to go out and do in the field. For concerts, you studied things and then you applied them to products. You didn't go out before a show and tune a system. You did that by ear, or most people did. And Don was desperate for ways to make his sound systems more linear and sound better. And he went piece by piece, gain stage through gain stage, trying to find ways to do that. And one of his biggest accomplishments was finding ways to time align his sound system. And that's a registered trademark. So align in time his sound systems so that they sounded tighter and more controlled.
Okay, we have one last question for today from, I guess, Rustifer Matt. I'm an educator overseeing a cement recording space around 32 by 40 feet, which is completely untreated except for a thick horseshoe curtain. What are my first steps for treating the space when budgets are typically fairly limited, between 15 to 40K maybe? If it's done bit by bit, what are some good resources for determining where to start? It's a space used for television as well as music production.
My good friend, I will answer this question, but just to be complete here, you can now see a picture of Don Pearson, myself, and the ever crazy isolators. And it's a little bit hard here to see you can see the rubber sort of bows out and the steel plates are a little bit impossible to see, but the pressure, this column on the top and this column never make a rigid connection. Those are the isolators between them. And that's wow. Don Pearson, and that's me. Is that cool or what? I think that was worth hunting for. Thank you, Mr. Briss.
That's incredible.
Yeah, it's a great picture. It's one of those things that you never get to see in a concert hall. And the funny thing is that I used to take people down there on technical tours, and I had a great time doing it. The problem was that it was not the the folks at Jazz at Lincoln Center, their insurance didn't like people being down there. Here's another tech tour that I did with Wynton Marsalis, myself, and one of the great blues musicians of all times, the great Taj Mahal. And that was a thrilling experience for me. And I took Taj Mahal down to see the isolators.
Despite the insurance company.
I said, screw it. I had Wynton with me. He could, they could yell at him.
Okay, so we want to get back to
his question. So
yes,
right. So he didn't give a ceiling height, but 30 by 42 is a nice sized room. And that's a great sized room. So here's what I would suggest is figure out your cubic volume, figure out your overall area. So 30 by 40, 32 by 40, you know that your floor is 32 by 40 or about 1,200 square feet. Your walls are going to be, whatever they are, if it's a 20-foot tall or 18-foot tall room. Your horseshoe curtain, if you look at the material, it should have a tag on it. It's probably a synthetic velour. If it's a heavy curtain with a chain on the bottom, it's probably 20, 22 ounce or 24 ounce. But you can pull the absorption coefficients and you can set up a spreadsheet. And you're more than welcome to send me a note, and I'm happy to send you a spreadsheet to do reverberation time. And what you want to look at is, okay, what configurations are people, what are we using the room for? If it's a choral room and everyone's singing in one direction, let's put absorption behind them. Let's get some diffusion above them and some diffusion where they are. Let's try and get rid of difficult reflections, like cutting across corners. Doesn't cost very much to do. Wood framing. One of my favorite designs, I can show you this, and this is relevant. Yeah, here it is. This should be cool. This is am I sharing my screen still?
We're seeing a console, yes.
Yeah, you're seeing a console. What this is prefab acoustical panels. This was David Hewitt's last truck called the Polar Express. And I designed this. You'll notice the cool yin-yang curve, by the way. Took me forever to find the client who would let me build that. But all this is cheap acoustical panels that were pre-manufactured. We put an airspace on the wall and I attach them, and there's just some trim to hide the seams. This is wood that we bought at Home Depot. It's a laminated fiberboard. So this is MDF. It's mid-density fiberboard with a wood facing on it. And it's just here to hide the top and bottom of, and this is a little soffit. So there's fiberglass on the vertical and fiberglass on the horizontal covered with fabric. And this is a very inexpensive way to do this because you can make these panels very inexpensively. And I think that for this project, all of this would cost, I want to say $200.
He had said that the ceiling is 12 feet high.
Right. In a 32 by 40 room, that's a pretty low ceiling. So you're probably going to have some 100 hertz type buildup. So you might want to look at putting some bass traps in the corner. And I would look at putting a soffit at least on 3 sides of the room. So if you look at this, just find the soffit pictures. Try to do this as quickly as I can here. This is soffits. There we go. Right. So now I just have to move this. Great, got it. Okay, so here are some pictures of some soffits, and this will give you, oh, why is it move stuff onto the wrong? Right, so this is a picture of a soffit with some lights in the bottom, and this is a rock sole type mineral wool absorption, and there'll be absorption on the bottom surface and on the wall and on the ceiling. So we're covering 4 surfaces. And here you can see a duct outlet, and this is duct liner board that I was telling you about, the black material. And here is a detail showing the mineral wool and some duct liner and some lighting. Here is a diagram where you have 2 inches of fiberglass here. You have fiberglass inside the studs. You can make this out of wood, out of aluminum track. It doesn't have any chipboard on it. So what you're able to do is see, for example, here, you can see a diffuser, some absorptive panels, some hard wall, and then soffit with horizontal and vertical. And this works really, really well in a podcasting studio. Here's a fabric track system. You can build fabric tracks or you can build frames. This is a little bit more expensive, but you can certainly do it. If you're going to run air through it without ducts, you need to use duct liner. This is a studio where this is a plate, low frequency plate absorber. This is a mid-frequency, mid-high frequency diffuser. This is a mid-high frequency diffuser. There are duct outlets here, and then along the underside of the soffit. This is Bruce Botnick's recording studio in Ojai, California. And Bruce is one of the best engineers I've ever met. And what a great guy. I'm very fond of Bruce. I think he's a wonderful person. And what an amazing year. Oh my God. I sat at a console trying to mix an album that I was working on for Ali Jackson, who's jazz drummer. And in 5 minutes, Bruce made me feel like an idiot. He was just so much better than I'm ever going to be behind the console. It was very humbling and pretty wonderful experience to sit next to him. So I would look at trying to find enough low frequency absorption so that the low frequency numbers are 1.35 higher than the average of the 500, 1K, and 2K. And literally the equation for reverberation time is really, really simple. You need to know the volume, the surface area, and you know you're not going to put absorption on the floor that's substantial. I mean, a carpet takes the life out of it. I like wood floors. You can always add a carpet under a drum set if you need to, or it's easier to add absorption than to take it away. So I like to keep floors hard. But I think that's worth talking about. Anything else before we finish up?
I first want to thank you because acoustics has changed so much in my career. I mean, when I first started, we thought, hey, we're getting great acoustics by putting egg crate on the wall.
And unfortunately, I was part of a litigation where they burned down a bunch of people doing that. So I'm really, I hope the people who tuned in found this to be a useful discussion. I'm easy to reach. All I ask is that you try to solve your problem first before you call me. So, or text, doesn't cost anything to give me a call and say hi and send an email. This is a particularly difficult week. I leave here and in 40 minutes, I'm tuning the system at Pier 17, which is an amazing facility in New York City. It's a rooftop concert venue for 4,000 people. With the Brooklyn Bridge behind the stage, and the bands are looking at the Statue of Liberty, and we have neighbors that don't want to hear us in Brooklyn across the river and in the Wall Street area downtown. And we have a adaptive beam forming sound system where each of the 12 boxes per side have 22 drivers. So it's a pretty complicated system, but it really, really, really controls sound dispersion.
Well, Sam, I'm going to hold you to this because I'm going to invite you back to actually, maybe you can do a video tour of that facility one day.
I would be thrilled. I love Pier 17, and I encourage everyone in New York area, or if you're coming to New York, come see it. And again, I hope this was worth your hour. Have fun. All I ask and all I really want to say is I've been incredibly lucky to not have to do anything else in my life. I mean, this has been my job. And I started mixing bands in high school and college and got to meet Russell Johnson and work for him. And I've gotten to meet a lot of great musicians and people I've really idolized. And I've gotten to meet some great engineers, almost to a person, who have been helpful and friendly and answered questions. And I'm trying to pay it forward. And I feel incredibly lucky. And recently winning this Lifetime Achievement Award is just like a little overwhelming. You know, it's been great. And so I want to say thanks to everyone. And, you know, acoustics is not something to yell and scream about. It's something to discuss and learn and move forward. Oh,
Well, thank you again, Sam.
and I've been using a really cool microphone today.
Yes, is that a 44B?
That is a 44A
Okay.
with the high output mod.
Yes, I was going to take out my 77, but I didn't want to get into a mic war with you. But thank you again. And I do want to remind everyone to become members of the AES New York section Facebook page. And also, we have just started a LinkedIn page. So if you type in Audio Engineering Society New York, you can become a member there too. And this way, you'll get all of our information in two places. And hopefully in a few months, we will be back in person, because this isolation is not good. Acoustically, it's good, but not good humanly. So let's all try to get better. And thank you again to Angela Piva, Roe Shamir, and the whole New York AES committee for this. And this has been the New York Audio Engineering Society. Thank you.
Have fun, guys.